Good morning, everyone. Today I will give a presentation of our paper, Vegeta, Enabling Parallel Smart Contract Execution in Leaderless Blockchains. My name is Yongqi, and this paper is the joint work of Tianjing, Yiming, Ruofan, Jingjing, Guangtao, and Shengyun. Firstly, I will discuss our motivation. In the blockchain system, we have two scenarios, leader-based consensus and leaderless consensus. First, in leader-based consensus, one leader node gathers transactions in blocks, making proposals and coordinating consensus. When the consensus completes, other nodes execute transactions in the sequence defined by the leader node. The leader node takes heavy duty in making proposals, which makes it the bottleneck of performance. In leaderless consensus, every node is able to make proposals. Such proposals are ordered during consensus, and after consensus, every node executes transactions in the sequence defined by the corresponding proposals. However, when making proposals, nodes don't have accurate execution environment, resulting in inaccuracy of their schedule of transactions. Then we can give illustration to the accuracy of the execution environment. First case is the leader-based consensus. During proposal phase, the leader node puts TX1 in block 1. TX1 deposits 100 into account D. After processing block 1, leader node puts TX2 and TX3 into block 2. TX2 deposits 100 into account A, and TX3 calls the function conditional transfer. Here, the function conditional transfer is an operation called by a bank. The bank will check the balance of the account. If the balance is greater than some threshold, it will transfer the balance to the receiver. We can see the procedure code. In this example, we set the threshold to 100. After TX1, the balance of D is 150. It's 150. When executing TX3, there is enough balance in account D, so TX3 will continually transfer balance to the account A. We can get the read and write sets for the above transactions. TX1 writes key D, TX2 writes A, and TX3 reads D, writes D, read A, writes A. Then we propose to the consensus. After the consensus in the execution phase, all nodes process block 1 and block 2 in the same sequence. Every node processes the TX block 1 and block 2 in the same sequence with proposal phase, and the execution results as is read and write sets for all transactions are the same with proposal phase. So we say that the execution environment is accurate in leader-based consensus. However, the situation in leaderless consensus may be different. During proposal phase, node 1 processes TX1 in block 1, and at the same time, node 2 processes TX2 and TX3 in block 2. In the view of node 2, it doesn't know the execution of TX1. When TX3 is being executed, the balance in account D will be 50. As a result, TX3 will not perform transfer. TX3 only reads key D. Under such situation, node 2 will make the schedule that TX2 and TX3 can be executed in parallel. But during execution phase, all nodes will process block 2 after block 1. Then when TX3 is being executed, the balance in account D is 150, and TX3 will perform the transfer. The execution results of TX3 will be reading A, reading D, writing D, reading A, and writing A. If one node follows the schedule made by node 2 to execute TX2 and TX3 in parallel, there will be a conflict. the execution result of proposal and the execution phase is different, and the execution environment in leaderless consensus is inaccurate. So our paper aims to give a framework tailored for leaderless consensus, increasing the execution speed of transactions, and at the same time ensure the correctness of parallel execution. So we propose speculate order replay framework. The abbreviation is SOR. Although in leaderless consensus, proposals do not have accurate execution environment, they may still obtain crucial and roughly accurate information about transaction conflicts. Read and write sets, that is the read and write sets and the program traces, which can greatly help maximize the parallelism. Therefore, our framework allows each node to speculatively execute transactions before consensus. There are three phases in the SOR paradigm. First is speculation phase. Nodes pre-execute transactions to analyze dependencies and make schedule. The second is the order phase. Proposals are ordered. Proposals are ordered using consensus. And the last is replay phase. Nodes replay transactions, follow the schedule, and apply re-execution to fix the inaccurate speculation. So we can have an example. In the system of 4 nodes, we take node 1 as an example. Node 1 processes speculation on block 1 and makes a proposal. After consensus, it gets ordered 4 blocks and replace them one by one. When replaying old blocks, node 1 can also start speculating block 5 and making a new proposal and repeat the same operations. We also instantiate our framework through Vegeta. Vegeta is a transaction-level concurrency control protocol and follows SOR paradigm. We pre-execute transactions and build DG. The DG is dependency graph in the speculation phase, and then order proposals using consensus. When replaying, we follow the DG to execute transactions and validate their read and write sets. If some transactions read and write sets changes, we say that it is invalid and re-executed it at the end of the block. In speculation phase, we have to first mention the dependency chain problem. In a dependency chain, for example, TX1, 2, 3 all write key A, so they have to be executed serially, which decrease the parallelism of execution. If we execute transactions in dependency chains after the transactions can be executed in parallel, there will be a long tail of serially executed transactions. So intuitively, we give transactions in the longer dependency chains with higher priority. Such transactions should be executed earlier during the replay phase. For example, we have 4 transactions in one block. They have a predefined order of TX1, 2, 3, and 4. We first pre-executed all these transactions and obtain their read and write sets. Based on different keys, we can form dependency chains and order them according to the chain length. Then we adjust the order of transactions, give transactions in longer chains with a more forward position, and the order is changed to TX1, 3, 4, and 2. Then, according to the read and write sets, we analyze the dependency relationships between transactions and build a DG. The dependency graph is a DAG because all transactions have a predefined order. There will not be a cycle. There are 3 types of dependencies. That is write after write, write after read, and read after write. For example, TX1 write A and write B. It don't have dependencies with previous transactions. And TX2 just read D, so it doesn't have dependencies. TX3 write key A, it has WAW dependency with TX1, and TX4 read A, write B, write C. What's wrong with this? It has WAW with TX1 and RAW with TX3. After the speculation, we make proposal of transactions and the information obtained in speculation and process the consensus. Then in replay phase, we execute transactions batch by batch based on the schedule showing in the dependency graph. And we need to validate the execution results of transactions. If read and write sets of some transactions are different from that in speculation, we should re-execute them in serial order at the end of the block. We define that transactions can be executed based on two rules. They don't have WAW dependencies with previous transactions, or they don't have both WAR and RAW dependencies. Such rules reference area to improve the parallelism of execution. We briefly illustrate batch by batch execution. Given the dependency graph, we can group transactions into different batches. Firstly, TX1 and TX2 satisfy the above rules. They are grouped to batch 1. When TX2 and when TX1 and 3 complete, TX3 and 4 satisfy the rules. They are grouped to batch 2. Transactions in the same batch can be executed in parallel. Then we should process in detail. Recall the function conditional transfer. If the balance of D is greater than 100, the balance will be transferred to A. This function is called in transaction TX2. Note that during speculation, the balance of D is 50, so TX2 only reads key D. Following the dependency graph, TX1 and TX2 have no previous dependencies. They can be executed in parallel. We assume that in the previous block, some transaction update D to 150, which is not observed by TX2 during speculation, but it's observed during replay. Then the execution result of TX2 has changed. It additionally writes key A and key D. So TX2 is invalid and needs to be re-executed. After that, in the dependency graph, there is only TX4 and TX3. And they also meet the rules, so they can be executed in parallel in batch 2. After all transactions are executed, we re-execute the invalid TX2 at the end of the block. Some changes in write sets don't necessarily introduce new dependencies, so we design optimizations to reduce the re-execution rate, which is described in our paper. When evaluating the performance of a design, we constructed a testbed on Amazon EC2 platform. In the multi-node experiments, we set up at most 10 same instances. We also chose the real Ethereum data as our dataset. We constructed our datasets with different rate, date, and length of blocks. We highlight our performance in multi-node setting, which is one of the main contributions of our solution. We can see that in the area is the state-of-the-art concurrency control protocol. It executes transactions in parallel without any prior knowledge. During execution, it has to validate the execution results and detecting conflicts dynamically. Those conflicted transactions have to be aborted and re-executed. In our evaluation, the aborting rate of area is pretty high. Transactions need to be re-executed, accumulate, and the execution in experiment is endless. So we introduced area FB, which means area fallback. In the area FB, we use our design to execute transactions that is aborted by area. Then the aborted transactions will not accumulate, ensuring the experiment can successfully finish. As the result shows, the speedup of our design Vegeta is about 6.5 times for 4-node setting and 6.9 times for 10-node setting, which is higher than area FB, showing satisfying performance. In 10-node settings, we can process 10 blocks in one consensus procedure. The throughput is higher than that of the 4 nodes. We also measured how many transactions should be re-executed in our solution, showing as the re-execution rate. The re-execution rates are low in both 4 nodes and 10 nodes. Re-execution has low influence to our performance. In our paper, we also test the performance in a single node, and we conducted ablation study in Vegeta. We also made comparison between leader-based and leaderless consensus. We also briefly simulated 2 cases of Byzantine attacks. So in conclusion, we designed a speculate order replay paradigm to accelerate the execution of transactions and instantiated it with transaction-level concurrency control protocol Vegeta. We can leverage the information obtained in speculation phase to enable efficient parallel execution in replay phase. Tailored for leaderless consensus will allow nodes to process speculation and replay at the same time. We also apply re-execution to guarantee the correctness of execution. Thanks for your listening, and I'm glad to answer your questions.